So we could put this on YouTube. And one more thing, I have to hook up and then we will start.
The simplest way to unmute yourself is press down your space bar when you want to talk.
Excellent. Maybe you can also talk about where the zoom button is so you could zoom in on the screen. Okay, ready to start. Welcome everybody to the Propeller 2 live forum. Today we have Spin 2 Debug with Runtime Expression Reporting from Chip, who's worked very hard on this for the past month. Chip, you are here, right?
I am. Can you see me, hear me?
We got you, yeah. Okay, so before you start, a couple things. First off, if you want to download Peanut today, here's a link for it. Gonna drop this in the chat. If I could find the chat button.
So, John, you noted that Windows said it had a virus in it.
Yes, on download, and I managed to use Firefox and kind of work my way around it and get it to download. But when I went to copy the files from the zip to unzip them, I got a complaint there. And when I could copy the files into a new folder, and within 2 seconds, Peanut would be obliterated by Windows Defender. And for a couple of times, it said, it pointed out the name of the virus, and I'm trying to get back to that so I can show you what it's saying. But
it's likely because the executable is not signed correctly. So it'll just, Defender will default treat it like a virus.
I've seen that, but it's being much more aggressive this time. It's actually removing the file within seconds of me putting it there.
This is for installing Peanut, John?
Yes.
I downloaded the zip file. I got it down, and when I did the transfer, I turned off the Windows app and ran it, and then I ran it again with it on, and it choked on the exe file. That's the one that all of the rest of them copied without it complaining, and it was the Peanut exe.
So you have complaints, but it successfully ran.
I haven't run it. It's just that's the one that it said it was concerned about.
Yeah, in the past, I've had that too, and you can say go ahead and run it anyway, and then Windows will allow it from there. But at least for today, this version of Peanut, my version of Windows, I'm running Win 10 Pro, is being very aggressive with the Peanut T file.
Yeah, I just that's why I haven't tried to run it yet.
Okay, well, let's carry on. We'll see the demo and then we'll come back to this. All right, for those of you who've got Propeller 2 Evaluation Board Rev C on order, there are 40 or 50 of you. Those are in manufacturing, just coming out. We're going to ship them between Friday and Tuesday. Right, so they're done, they tested out fine. And then this display, which I keep chatting about, they've arrived and we will have them ready to go on Tuesday as well. So if you've ordered both of those pieces, you can contact us to combine the orders. And then thanks to Roy and some other forum members, I've added this cable to the display. Just be sure you pay attention to the polarity. Red is not power once you're connected to the display. And I think JMG pointed out you can pull these little wires out and then plug them back into the connector, but we'll leave that up to you. Also, Rich is revising this enclosure so that the boards fit. When I tried to use it with the video board, I had a conflict, and he said that, well, everyone's working around it, but I talked him into revising the design because I want it to be 100% compatible with our boards. And speaking of, we're out of those. We're building 100 of them. It looks like they'll be back in stock the first week of August. One of them depends on Chip making a decision. Chip, make a decision. Quartzel board, far right.
Right.
waiting now for you. And Johnny Mack is going to add another board to the queue. It's an RS-45 board that'll be available separately from this, and we're going to make that as well. I mentioned this last time. We're teaming up with Micro of Serbia, who makes thousands of little click boards, and we expect at some point to have an adapter. We've already made an adapter for the P2 eval board that connects to the click boards. So we're going to bring that to our shop soon, so you could use the clicks. And this week, since we last met, 2 revisions to Spin 2 objects have been added to our GitHub. The first one is Johnny Max PWM, and then Von Slarvash made a fix to the SPI object. So that's in there. Going forward, we're building a new website at Parallax, and you're all going to like it because it's going to bring commercial product applications back to the forefront of what we do, side by side with our educational products. So it's going to serve both of us. And we need your applications, your products. If you make a product with the Propeller in particular, we want it. We'd like to showcase it here. We need a description of what it does, why you're using the Propeller, and some good pictures. Next week, we have Team Oz talking about MicroPython, Tubular, and OzProp Dev. And Chip and I and Jeff have met with this group several times in the past 3 or 4 months to look at what they're doing and give them some input. And this will be a neat presentation. And then coming in September, we have a presentation from Jeff and Michael, and it's a couple parts to it. One is the Propeller tool, using it, and the other is wireless programming of the P2 using our WX module. So it's pretty cool. So that'll be in September, but we have three or four voids through August where we can accept presentations. I'm interested in getting one from John Titus about smart pins. Hopefully Johnny Mack with his P2 programming philosophy, and maybe Richard Morrison, the chemical engineering scientist in Australia. That's it for that. Chip, moving on to you.
All right. Okay. So let's see. I'm gonna try to share my screen here.
Yep, I'm gonna make you co-host as
share
well.
Screen. I just want to show an application. Okay. So can everybody see a peanut window?
Yep.
Okay. All right. So you see here, there's a very simple little program, right? It just does a loop and then does this debug statement. UDEC means unsigned decimal I. So before I run this, I want to show you, I've changed the menus around here so that we have, it's kind of simplified. We have the view, compile and view for both debug and non-debug. Then we have load RAM for both debug and non-debug, and program flash for both too. So I'll do first just this thing. If I compile this program normally, okay, can you see the little status window? Whoops, hold on. Is the status window inside my other window?
Yes.
Okay, so you can see here that we have the interpreter's 4K and not much going on. Now if I do Control F9, it shows, cannot make a visible window modal, process stopped. Oh, it doesn't like, I think I blew up. Okay, can you guys, gee whiz, what happened here? Hold on.
This is the best way to test new software.
Yeah, well, it's like it won't let me close the app, which is kind of weird. Okay, I'll just start another one here.
The other example, did it have a delay in there after the debug?
No, it got tangled up with the Zoom thing. The Zoom had some kind of screen issue, and when I tried to move a modal window into my thing, I think Zoom conflicted with it.
Jeff, as a backup, maybe you can get it running in case Chip has trouble.
Okay, so I think I need to reshare. You're not seeing anything again, right?
We do see the memory map and then Peanut.
Okay, let's see. I'm not even sure
Why
where
don't
that's
you
coming from.
click on stop share and then you can try to reshare. Maybe that'll
Right.
fix it.
Okay. All right, now, okay, here we go. Sorry about this, guys.
I think Zoom doesn't like his monster rotated display setup.
Yeah, we'll never see anything if he shares his whole display. That's when people stick their nose against their camera trying to see.
Okay, so now you can see my little window, right?
Yep.
Okay, so I'll load the file again. All right, so we have here a little loop in this thing. So if I do like a control, if I do an F10, it will run. If I do a control F10, it will bring up the debugger. So I'll do control F10. No hardware found. You know what? Something is blocking my port. There's another instance of this app running that I need to kill somehow because it's got my port all tied up. Boy, oh boy. I'm going to have to go into, do I have to go into the device manager to get rid of this thing?
Do Control Alt Delete and do Task Manager.
Or that's what I mean, Task Manager. Yeah, okay, so I'm in Task Manager, and let's see, where is it? Here it is, End Task. It says not responding. Well, how can I get rid of it if the OS can't kill it? Peculiar situation. Any recommendations?
Well, if you want to restart, you could. And Jeff, do you have it up and running as well?
Chip, if you want me to show it, I got it running here.
Okay, all right, let's do that.
I'm trying to get it running. Let's go to
Everything that's gone wrong has gone wrong here. Everything that could have gone
You
wrong.
might need to close Zoom and reopen it. It might have locked the app
Yeah,
that it was
yeah.
sharing.
Yeah, I suspect that's what's happening.
Well, what we could do is have Bob open it. I've made him co-host, and Chip, you could chat him through it.
Okay, let's try that.
Yeah, okay.
So Bob, did you see a share screen on the bottom? You should have that now.
Share screen. See,
And I
yep.
think what you want to do is choose the application, Peanut, or you can share the whole screen if you don't have a super high res display.
Okay, let me see, share.
Meanwhile, I'm going to get out and I'm going to jump right back in, okay?
Oh, that looks good.
Yeah.
Hey!
Oh, look at that. Okay, so we'll retrieve Chip.
Okay,
But we did get Chip to show up, and that's half the battle.
I got it on the screen there. Did you see it?
Yeah, you got a
Yeah,
wonderful setup. Chip's internet connection too is several megabits per second. It's really not that good.
He's probably also still on Wi-Fi out there in his office, right?
He is.
That knocks a bunch of overhead off the top too.
I might start sending him to the library for future presentations.
Just buy him a 100-foot cable to run from his house to his office.
Oh, I see. He's got the wired connection in the house and then Wi-Fi repeaters going out to his barn.
I think so. That's what he was a few years ago last time I was there. I'm not sure if it's still that way.
Ken, while we're waiting for Chip to come back, can you just explain what this screen is showing us?
So this is the first time I've seen it. It's just debugging. I think it's running that spin code he has.
Right there,
Yeah, just showing the decimal value of the I variable.
All right,
Yeah,
so
this,
if you had multiple variables, would all of the variables show up on this line?
So my preliminary understanding is you can format this just like you could for advanced parallax serial terminal type displays, where you could put in a number of variables and position them too.
see that line of code in the debug command that says udec
Yeah.
That's what's specifying what to output. So it's outputting the name and the value of the I variable in unsigned decimal format. So you could add more variables in there too, as far as I understand.
It's almost a PBasic looking formatter.
But this is the first time I've seen it too. Chip and I have talked about it many times.
The one thing I was wondering about was if you had multiple cogs going, would you specify this debug per cog, or does it print out everything from all cogs?
Yeah, yes, you can specify it for each cog.
Okay.
And
Does it
that's
have to
what
be
the
specified
cog
for
zero
a
that we,
cog?
the cog zero that we see there is so that it, you can figure out which cog or see which cog the debug output was coming from.
Okay.
But it seems like, looking at the code, Jeff, that if any cog uses debug, then all the cogs could use debug, and the debugger knows where the message is coming from. You just have to add a debug line in your cog code.
Right. Yeah, I believe that's correct. But you don't have to have a debug in each cog, as far as I understand.
No.
The way it works is you can have multiple debugs across various cogs, and even though they're all using the same serial port, they multiplex their sharing of the port through, I believe it's the lock bit 15, so that they don't clobber each other. Hopefully Chip's coming back soon. I can't get mine to download.
Okay, we've retrieved Chip. He's just now getting reconnected.
Okay, all right, can you hear me?
Yeah, so don't do any screen sharing because you might bring it back down, but Bob has it up.
Okay, Bob. All right, so what you see here is even if you have no debug statements in your program, the debugger tracks all cognits. So as cogs are started up, not as they're stopped, but as they're started, the debugger is invoked and it spits out a little message saying, what's the code address and the parameter address, and then was it like a load style cognit, or was it a jump where it just jumped without loading to some location? Could be in the cog or it could be out in the hub. And then as it receives these statements, the UDAC I, you can see it printed out these things. So you can take any application you have and just do a control F10 with it, and it'll at least print out when cogs are starting and stopping. And you can use the program flash ones also. Now you can add quite a few things to a debug statement. See where it says UDEC sub I? In front of that, could you type maybe like hello in quotes?
Here? Right there?
Yeah, right there. And then put a space so it spaces out. And then put a comma after the last quote.
Oh.
Yeah, that's right. Comma there. Oh, comma.
Oh. Oh. Yeah.
That's a semicolon.
Oh, comma, gee.
There, now, okay, now do a Control F10 on that.
All right.
Okay, so you can see you can put whatever kind of text and whatever kind of reporting you want into a debug statement. And as it's encountered during execution, it spits out whatever your message is about. And the way this thing works is it gets squirreled away in the last 16 kbytes of RAM, and then it loads your it moves your application down into the base memory where it was going to run if you didn't have the debugger. So it sets up the environment like your application is going to run from scratch, but it's already installed all this stealthy debug stuff that we have all this special silicon for. So once all that stuff is in place and the debugger's tucked away up in that protected memory, the only way that memory can be written now is from within debug ISR. So as cogs start up and then subsequently generate these debug interrupts, the messages come out. And the messages are fast. You can see that 0 to 99. How about change that to 99.99?
Okay.
Yeah, now run that. It's spitting out, there, I got to the end. So it actually did that faster than what we saw because it was queuing a lot of that serial as it on the PC side, because Windows isn't that fast at displaying stuff. So a smaller debug message takes about 100 microseconds. So that means that your program is interrupted, whoops, by hand. Your program is interrupted for about 100 microseconds when you do, a smallish statement like this. Now, if you want to slow down, before the last parenthesis, can you put a comma in there?
Right here?
Yep. And then type DLY for delay. And then in parentheses, put like 250. Yeah, now run that. You can just go Control F10.
Chip, a question from Jen Granville. Can this print a timer in each loop to show how much time is used by debug?
How much time is used by debug? You could construct something like that. You could, if you do like a variable assignment within a debug statement, you can record the time and then reference it in the second debug statement later on. Okay, so now hit escape to close that debug window. And then do a Control I. And this will show the debug. So here you see the debug data. So what it does is it does this thing in two pieces. It inserts a minimal amount of code at the point where you have the breakpoint in your spin program. It's basically a 3 instruction sequence. You see the 44 there, and then the 08, 01 in the upper section of data. That's the whole debug statement. And so it's taking, let's see, what else is it? It's pushing a value also. So it's probably taking the FA is an instruction, and then the 44080, and that makes up the debug within the spin code. Then down below, you have some distilled information that is used for that watch point that gets tucked away up in the debugger database that's in that upper 16 kbytes. So it's set up to have really minimal impact on your Spin 2 program. So there's not a lot of code the interpreter has to run through, or it's just the bare minimum. And then the longer record is stored out at the end of memory in the debugger. Now for PASM, for putting debug statements into PASM code, it's just one instruction. There's nothing else. And then the entire command string that the debugger looks at gets put into the debug data. So for PASM debug statements, it's just one instruction. And technically what it is, it's a break instruction. It's a break with an immediate 8-bit number. And that 8-bit number references the record that's stored away in the debug data. That's how all these things work, so that it knows, you know, what definition to look up to print your debug. Now, can you open the file called, let's see, it's called spin2 debugger. Okay, now go to the very, now this is the actual debugger program. In case anybody wants to look at it, this is like everything you need to do to, you know, have breakpoints that are stealthy, that go in, do stuff, and then return to the user program like nothing happened. The only thing the user sees is that some time was missing, but there's no other state information that's disrupted. So if you go to the very end of this file, there's a big list. You can just do like Control End to get all the way to the bottom.
Right. Whoa.
There, now we're almost there. So there's a list at the end of this thing. Try typing just Control End. There you go. Okay, so these are all the different number printing formats. So I had to come up with some names that are, you know, kind of formulaic, not too verbose, but also don't infringe on likely namespace for other things, because these are always like reserved words that are used by debug. So if you go up, so you see there's the unsigned and signed binary, and then go up a little bit. You could hit page up and then start doing up arrow. There you go. We have the hex, signed and unsigned, and then decimal, unsigned and signed. Okay, go down just a little bit, because there's some other commands. Okay, there. So we also have these conditions, if and if not. And what those do is those gate the remainder of the debug command. So if a condition is true, that whatever comes after that will be displayed in the debug command, and converse for if not. But the special thing about these is if they are put at the very beginning of the debug statement, they'll actually inhibit the entire debug statement from printing. So nothing's going to get printed, which is nice, because sometimes you want to filter and look for something of interest, but you don't want to have 1,000 messages where somewhere there's something you want. Because I was thinking to make this kind of conditionality, my first impulse was, well, I should probably have like an if debug block construct. But then what happens is it starts to get bigger and bigger, because the way this thing works is the debug statements under a normal compilation are completely ignored by the compiler. They're just skipped over. But only when you compile for debug do these debug statements become incorporated into what's being compiled. So this allows you to put the filter into the debug statement, and we can demonstrate that here in a sec. But otherwise you see there's the delay, the DLY that we use, and then there's the Z string and L string, and those you just give hub pointers for and a length for L string, and it will print out an ASCII string in quotes that sits in hub memory. So you have, oh, and you also have arrays. So you can, from hub memory and register memory, you can print arrays of registers, bytes, words, or longs in any of those number formats. And then you can print out 0 strings and fixed length strings, and they come out in quotes. So can you please load up again the first program that we had called Debugger Demo? All right, and you can change that back to, let's change that back to 9. Or the 999 back to 9, so that's going to be, you know, small. Now before the quote hello, can you put an if in there? And then in parentheses put I&1. instead of the exclamation point, use a shift 7.
Oh,
That's right. And then put a comma after the right paren there.
comma where?
After that right parenthesis that's nearby. Oh no, not in there, but after the parenthesis before the quote. Right there, yeah. Okay, so what this is going to do, it's going to do a conditional thing where it's going to see if I is odd. If I is odd, the message will go forward. If I is not odd and that thing is negative, nothing gets emitted. So you can run this by pressing Control F10. There, so you see it just emitted messages that pass the if test. Okay. Let's see, I'm looking through my list of stuff to talk about. So we can try, why don't we try like printing with another number style? How about use like ubin instead of the deck? So you can hit escape to close the debug output window.
Chip, if you want, you could try to share your screen again.
I'm a little afraid to.
Okay.
This is working out fine. I mean, we can do a lot with this. So where it says udeck, why don't you put like uhex_long, and then we can print out in 32 bits. Oh, yeah, okay. That's right, keep going. Now where it says UX, make it UHEX.
Okay.
Right, now Control F10 that. You just hit enter. Yeah, so you can see, now let's just why don't we do an array really quick? So how about uhex, let's see, hit escape to close that thing. Array, so uhex_array long. And then put an underscore right there. And then after the I, put maybe like a (4). Right, now, so that's going to take from I, actually it's going to use the address of I. So if we want to see I, how about put an @ sign in front of the I, and that'll give us the address of I, because right now we need an address in hub memory. So @ I instead of just I.
And Chip, it's uhex_long_array.
Oh, okay, sorry. Huh. Yeah. Okay, so put that @ in front of the I, not the 4. And then like Jeff said, I gave you the wrong name. So switch the words long and array. There you go. Okay, now, so we should see an array of 4, and the first element should be I. So if you hit Control F10, yeah, so you can see there's I, and then there's the data that was following I. If we pointed to a string, it would put the string in quotes. One other thing we could do, where it says uhex, hit escape to close that. Put an underscore right where the cursor is, because every one of these names has an alternate form where you can add an underscore. And now run that with Control F10. And what it does is it omits the name. So it simply prints the data without the name. So there, in case you wanted to put like some special header before. So it kind of can act in a generic way so that you can actually make your own custom messages that say whatever you want, but incorporate data. Okay, so let's see. I had another one that was printing out quickly. Change that. Now we're only running at 10 megahertz, right? We could put 300 megahertz there and it would actually, the baud rate would be the same, but the time between messages would go down quite a bit. Because at 10 megahertz, we're not that high, but if we get up to like, 100 megahertz, 200 megahertz, the messages are really fast. Let's see. Do a control F9. Okay, great. So you can see it's inserted the debugger, right? And note that the object is 32 bytes. So close that and then do a normal F9. So it's 20 bytes. So it added 8 bytes to have that debug stuff in there. And now the debugger is no longer present at the end of memory. So where those 8 bytes came from would have been from referencing the, it had to compute I ended with 1. So that would have been 3 bytes, and then 4 bytes for the later reference of I, and then we had 3 more bytes for the whole debug instruction. So these statements don't add too much, but it also made more data back at the end. So get out of there and hit Control I, and you can see what it built for the debug data. Yeah, so you see that record is longer. You can see the word hello in there. Now for PASM, have you got a PASM program that you've been playing with at all that you could load in here?
Me, no.
Wonder if we could, how about this?
Wait now. If I can get out of here.
Chip, you can copy one in chat for him.
You know what? I know what we can do. Load the program that's called ADC to millivolts.
Oh, this one here.
I didn't give you the name exactly, but you see it there?
Is this one ADC to VGA?
Yeah, that one.
It's up.
Okay, I don't see it here. It's like the screen's not refreshing.
Okay.
Oh,
wait, no. Maybe I get rid of the old one first. Oops. Ken, can you share again?
are you turning him back on, Ken?
We can't hear Ken.
Oh, sorry. Yeah, you have to activate yourself. Green button on the bottom.
Okay, here we go. Okay, where were we?
And then you have to open the app and then share the app. There it is.
Okay, VGA to millivolts.
Okay, let's see if we can get this display a little better. So Bob, go back to share screen and then share the share the application Peanut. And I think we'll be able to see this better.
I'm not sure what happened here.
I think you got to relaunch. Where'd it go? There we go.
Can you see that?
Yep, yep. Okay, so go down a page or so. Let's get into the little bit further down. Okay, now oops, go back up a little bit.
So because he's sharing the display, to zoom it, go up to view. Anyone who wants to see this better, go on top to view options and then choose zoom ratio under that menu. And you can zoom in on your machine.
Okay, so go up a few lines. Okay, now let's see. Okay, so see where the if not carry is, the RETI1, go right below that, and we'll make a line there. So it falls through that thing. Yeah, tab over right there. Type in debug, and then left paren, UDEC underscore long array. Oh, with an underscore, sorry, between long and array. And then that's UDEC, UDEC, not UDAC, sorry.
UDEC, okay.
Yeah, there you go. So unsigned decimal long array, and then go to the end there and put parenthesis, other parenthesis. Yeah, and then type, let's see, pound sign samples. Okay, so when you do a debug statement in PASM, so samples, and then comma pound sign 8. And then 2 right parens. Okay, so when you do a debug statement in PASM, you have basically like assembly operand rules where anything that's not preceded with a pound, declare it as immediate, is assumed to be a register. Okay, so this is different. It uses all the same commands that the spin one uses, but you can only deal with registers and constants. Okay, because in assembly language, that's really all you have. So, and what it does in this case, it's just going to put a break instruction where the debug is, and then it's going to build the record off in the protected memory at top. So it's always just one instruction. So do a control F10. Oh, you know what? Type event SE1, not in. SE1.
I'm not sure what you're saying. Event?
Event, yeah, event underscore SE1. Yeah, and get rid of the int underscore. All right, now control S to save, and then control F10 to run with debug. Okay, you can hit escape to get out of that. We're not getting the right information. Let me see. Let me look. Uh-oh, my, boy, how do I get my command bar back? It seems to have disappeared into the abyss here with Zoom.
Your command bar is usually underneath the Zoom display. It does go away and come back.
Yeah, how do I get it to come back? It's like
hover where you think it should be, and it will appear.
It's all the way across the bottom, but it's not doing anything. can I like resize zoom so it doesn't take the whole screen?
Yeah,
Yes.
that'll fix it.
Hit the escape button.
Oh, exit full screen. Here we go. Okay. All right. Okay. This is sanity has returned. All right. So let's see here. Let me just see what I put into that debug statement on my end. Yeah, pound samples, UDEC reg array. Oh, okay, UDEC reg array. Sorry, that's our problem. So instead of UDEC long array, up where we have that debug statement, so go down a little bit. A little more. Okay, stop there. Wait, a little further down. There. So instead of UDEC long array, make that say UDEC reg array, R-E-G. Okay, now Control F10. So see, when I made this program, these are millivolts that it's reading on 8 consecutive pins. And when I made this program, I had to have a whole VGA driver and everything so that I could see what was going on inside that thing. That's why it's called something VGA, because I needed a display mechanism. But now that we have this debug, this would have sufficed, and I could have just totally concentrated on, you know, the ADC stuff without worrying about giving it the video interface that I did. So it says pound samples for the address of samples, comma pound 8 elements. So those are the millivolt ADC conversions that the thing is maintaining. So hit escape to get out of that thing. Now do a Control L. Go down a little bit so we can see how many. Okay, there. So OBJ bytes 2564, and then go all the way down past all the data, and then you're going to see the there's a VGA driver in here and all kinds of stuff. Okay, nothing at the end. Now hit Control L again to get out of here. Now do Control I to assemble it with debug. So go down a little bit more. So it's 2564. Whoops, up just a bit. Now it's 2568 because that debug as a break instruction took 4 bytes, right? And then if you go to the bottom, you can see the record that it put into the memory up top. So go all the way down to the bottom. There. So that's the record. So you can see how it partitions things apart. Anyway, when the debugger starts up, it's as if your application is booting. All the silicon stuff we put in there is so that the debugger is very stealthy, that no one knows it's happening, and it lives in protected memory that nobody can write. So they can't inhibit this thing from working. So when the debugger starts running your code, it's as if the application is actually running for the first time. But the debugger got in there ahead of time and established itself kind of like a little parasite, then turned the host on, and then the whole thing runs. Now, there is one thing you can do. We don't have a demo program that uses multiple cogs, as far as I know. Wait, you know what? All cogs blink. Is that all cogs blink file in there?
I can dig one up, but I have to stop the screen share, I think. All cogs blink.
No.
No.
Because that one starts up a whole bunch of cogs.
Oh, no. Well, blink spin.
Yeah, that would just blink a few things.
Yeah.
This was probably from older distributions that I made.
Right.
So you know, it's not really critical, but what I was going to show is that you can define a constant called debug_enable, and you give it an 8-bit value. And those 8 bits define which cogs of the 8 are enabled. So wherever there's a 1 bit, that cog is debug interrupt enabled. Wherever there's a 0 bit, that corresponding cog is not debug enabled. But what happens is this thing is set up so that if debug instructions are encountered, but the debug interrupt is not enabled, it doesn't hurt anything because nothing happens. The break instruction in a PASM breakpoint, it does a break, but no debug interrupt occurs. So effectively, it's like a 2-cycle no-op instruction. And then what happens in spin is it prepares anything it needs to have on the stack. Then it does the break. And in part of doing the break, it pops everything. It adjusts the stack pointer back down to kind of effectively unpop everything that was put on there. And then it does the break for whatever specific code that break message was for. So it's harmless. So what you can do is you can run with debug enabled, but then only enable debug on special cogs that are of interest to you. While other cogs just get ignored and they don't even report when they start and stop because they're completely out of the loop. So if you had something that needed to be, super high speed and not get bogged down, you could turn debugging off for that guy. And if he encountered debug instructions, there'd be a slight overhead, but he wouldn't be making any messages, and you wouldn't know if he's starting or anything.
Yep, we have a few questions in the chat window. One of them relates to what you just said. So compiling without debug is the same as commenting out the debug function calls?
Okay, wait. Say that again. Say that again, Jeff, because I was reading. I didn't hear what you said.
Oh, compiling without debug is the same as commenting out the debug function calls?
Exactly, yeah. So you can leave them in your code. They're not going to hurt anything. Only when you compile for debug do they become incorporated. So no need to run around and uncomment anything.
Okay. And is debug a special instruction or a function? I'm not understanding how the debug parameters know the difference between literal and registered.
It's kind of a hybrid thing. Now in Spin 2, you can put method names in there and it'll actually call those, if you're putting together an equation or a value or you could put calls in and it'll do it because the debug's not, see, once it gets everything staged up and ready, and then it does the actual debug sequence, where at that point, it has all the data for the message is fixed. There's no more discovery involved. So it goes to the debugger composes the message, spits it out, and then returns. And by the way, go ahead.
Using debug with the 7-inch 800 by 480 display, could we write the values to that?
Sure, yeah. Yeah, I have in this distribution that the 800 by 480 spiral demo. But the thing about that program is it's like we could go in there and find a point where we could put a debug, but a lot of that stuff is like very high speed and it's all cycle counted. And so we have to put the debug in there at some innocuous point so it wouldn't clobber what's going on. Now, one thing about that delay that you can use, what it does when it gets to the delay can only be the last instruction in a debug statement. And what it does is it finishes sending out the string and then it releases the semaphore that's used to control among all the cogs. It's used to share pin 62, which the serial messages come out on. So it's really only stalling the cog that's doing the delay. It's not stalling anybody else's messages because it's already freed up by the time it starts doing the delay.
And Chip, there's several questions about the capabilities of this. Program breaks, single stepping, variable modification.
Yeah. Okay, so here's the thing. As a first crack, I made this thing. If you think about this, this is kind of simple to set up because it's all one way, right? You encounter these breakpoints that show data and then your program keeps running. It's not interactive, right? So to make the next level of this, where we can do single stepping, a whole bunch of stuff has to happen. Suddenly now we have to have some like relationship back to source code so that we could show, you know, symbolic source code that people recognize, tie that to addresses, get all kinds of, you know, click and button feedback and everything. So it ups the ante by, you know, several fold. So that I'm going to work on in the future, but I figured this was like the low-hanging fruit that uses all the debug mechanism. And it's like, you know, 80% useful compared to a full stepping debugger, because you can see at any juncture what's happening in your program, which is worth a lot. But the single step is a single stepping debugger is really good for learning. You know, then you can see what the code does, and you can learn very quickly that way. But if you know what you ought to expect and you have data reporting, then it's pretty good for debugging, I think. And it doesn't engage anything on the chip. It's just P62 is used. Same pin that's used to talk back during download is where all these messages come from.
And Chip, for people that like to have beautifully formatted displays like Johnny Mac in Parallax Serial Terminal, will this recognize cursor positioning, carriage returns when?
Oh yeah, you can put in, you know, 0, 4, 5 into the debug statement, and it'll you know, emit those characters in the serial string.
And I pasted the documentation into the chat for those who want it. So anybody have some questions here for Chip?
There's still some in the chat window that we haven't asked. One is it possible to also view hub memory from PASM debugger?
Yeah, you can use, so the long array and word array and byte array of any number type, those are hub. If you want to look at register arrays, you use the reg array. So just use the Z string thing, and it prints out a Z string. So yes, let's see. When you're debugging several nested of single stepping comes very friendly. Yeah, I see what you're saying, Tamayo. Yes. It would be neat to have that, and that's something in the future, but that's gonna it's gonna be a lot more programming than this was. But the good part of it is that the whole concept is proven. I mean, when we get into these debug interrupts for this debugger, everything is already kind of in play. You know, we're coming in, we're saving everything, we're sharing a serial port to communicate back to the host, and cogs are not stepping on each other's toes. And they go back to their business like nothing happened. So we have everything we need to make a single stepping debugger. The big part of the single stepper is that we really, I mean, it wouldn't be hard to make an assembly level version, but people are gonna want to see their source code. And that's when it starts to get more complicated. So it's not as trivial to make as this was.
There's another one. Is the debug window just a serial terminal?
Yeah, so for single step and VeriView, especially for learning, a simulator is good. So a P2 simulator would allow single step, but proper simulation of the peripherals is where the fish hooks lie. Right, yeah, that's complicated to do. I mean, the state, this chip is very stateful, and so are all the peripherals. So I wouldn't even like trust myself to make an accurate simulator for it, because there's just too much going on. There's too much minutia. So the way this kind of problem is solved these days is there are programs which take the Verilog code, which was compiled to make all the logic, and they convert that Verilog code into a C program with a front end. So when you run that simulator, you're actually running the hardware. Everything is identical to the actual hardware. It's just virtualized. So that would make a really nice simulator if we had that. And we could do that too, but that would be more of like kind of an offline system.
And Jeff asked one question you may have missed. Is that a serial terminal you're using in Peanut, the real basic one?
Oh, yeah, you know what? I started getting into this, and Windows is so slow. I mean, this thing can print out like 10,000 messages per second now and not skip a beat. But Windows is so slow that you can't have it draw the screen with those text rectangle commands every time. It'll take forever. So what I do is if you notice, all the text builds from the bottom up. So I size the window, and then at the very bottom, I output one line of text. And then when I have another line ready, I do a copy rectangle to copy that rectangle up to the whole next part of the screen, and then emit a new single line of text at the bottom. So it makes like a whole, scrolling display, but it's actually only printing ever one line at a time, which is about all you'd want to ask Windows to do because it gets bogged down pretty quick.
Chip, another question that I didn't understand, you explained it several times. Is the debug command transparent in regards to which cog the code runs, but it's running from a smart pin, right?
Okay, wait. Can you say that again, Ken?
Is the debug command transparent in regards on which cog the code runs?
Yeah, it's all, see, if you notice, this thing is working and there's no cog sitting around acting as a housekeeper or anything. Every cog that is doing one of these debug statements is doing it itself. And it's doing it within like a protected debug interrupt that can actually happen even within any normal interrupt. So when a debug interrupt occurs, it's right now. It's like a non-maskable interrupt, and it's not, once the debugger sets itself up, it can't be tampered with from the cogs. There's no code that a cog could execute that would like disable it or undermine it because it's off limits once it's set up. And that all happens before the application gets launched.
And Chip, this question Ray just asked, and I asked as well, using this with PST and Propeller tool, does Jeff have to do some revisions to Propeller tool, or is it just a matter of loading some code?
No, all I have that you see, that the black screen with the green text, it's simply taking in serial and printing lines as they arrive, and then scrolling, the rest of the view. So it's any serial terminal will do. I mean, you can take this and do a control F11 to program with debug for the flash, and then you could open up a normal serial terminal program, and when you start that cog up, it outputs those messages at 2 megabaud. So it's agnostic, but I had to make something that works within Peanut just to kind of get it off the ground.
So the plan is to give the same capability to Propeller tool.
Right, yeah, it's no big deal. We just route that data over to PST. But see, in my case, it starts up so quickly after the download. I mean, it's not maybe a quarter second from when you hit Control F10 and you start getting debug stuff coming out. So there wasn't time to wait for something to open up and then have a serial buffer overflow. So within Peanut, I just don't close the port after download, and I immediately start routing all the data over to that debug window. And then it just gathers up lines, and when it gets a line, it scrolls what's there and then prints a new line at the bottom.
And when will Propeller tool support this?
I don't know. I mean, it's not going to take Jeff more than a day or two. There's really not much to do. I mean, the only gotcha I see is that the data starts coming out right away. So Jeff could speak to that. I mean, do you have a buffer that's deep that can handle the half-second
Yeah,
delay?
I'm not exactly sure how I'm going to handle that because PST is a separate program, unlike was the case in the basic stamp editor where they're using it's all one. I had done some experiments in the past about serial port sharing that were really promising, but never implemented the code. So I'm hoping I can find that or find a different way to support it, maybe a back channel between the Propeller tool and PST so that it'll be seamless.
Good, okay.
So you're right. I think that's the biggest potential issue. Other than that, I haven't seen the code yet. Chip just published it, an hour or so before the presentation. So I have been doing some things behind the scenes in preparation for it, but I'm kind of guessing at what needs to happen. So I'm ready to work on it. Yeah.
Well, like Chip said, it'll take a day. We'll expect it Friday.
Yeah.
Thanks, Roy. Friday, 2 weeks from now, right, Jeff? I'm hoping to have this out there in some form or another in Propeller tool by next week at the latest.
Let's see. Dustin Isenga is saying, I'm not really grasping the concept myself, but would you rather use self-modifying code to change the debug statement in PASM, or would you just have statements to control what gets sent to debug? Okay, so you can use the if command within the debug statement in PASM. The trouble is the only thing dynamic you have are registers. So at this point, you can't say if register equals this. You'd have to have a register already with 0 or non-zero in it that you've computed just in the instruction or two before, so that when the debug hits, it can, or another way, actually maybe a better way, is just skip the debug instruction. So if you have a condition that you want to skip the debug in, the instruction before the debug in PASM, just put if whatever your flag condition is, skip #1, and it will skip one instruction after that. The only nasty thing about that is that it doesn't go away when you're not doing debug.
There's a couple questions here about how does this play with interrupt code?
So it works through any interrupt. I mean, that thing we did where we were looking at the millivolts, the ADC conversion, that was within a normal interrupt where we put that debug statement. So it works in mainline code, interrupt 1 code, interrupt 2 code, interrupt 3 code. It'll go anywhere. And when that hits, it happens. And nothing can stop it.
I think you had said earlier that the debug is like a non-maskable interrupt, so it's the top level interrupt for the hardware.
Right. Yeah, and it can only be its functionality can only be established within a debug interrupt. So because we configure all this stuff before we run your application, it's all sealed tight. When at the time your application runs, the debugger is already embedded. Your code can't stop it, and it's gonna do its thing.
One question I have is if you can change the ports. I mean, if my program wants to use the USB serial output to PST, can I put the debugger on some other pins?
I could make it do that. I mean, I could add a feature so you could have any arbitrary pin, spit out those messages.
I would think it would make sense to have some constant like you have for bitmap, which cogs should, also a constant on which pin used for.
Yeah,
yeah.
That's a good idea. I'm going to remember that because that's really easy to implement too.
I think so.
All that happens within the debugger program, so it's trivial to have it do another pin. Make TX pin settable via
Just
symbol.
with a constant like that, which cog should be used in the constant in the code, debug TX or whatever.
Yeah, debug pin, or yeah, debug TX, and then it defaults to 62 because we know we have facilities for reading that already. And then you can set it to something else if you want. Yeah, that's really easy to do.
It would be very helpful. Because when you say have a serial terminal sitting there or connected to some other, you don't want your debug there. Not. Yeah. So that's good.
I'm kind of happy this thing worked out like it did. It was designed to do this, but it had never really been tested as a system. But you know, I had to redesign the way the locks work in the new chip compared to the Prop 1, because in this new scheme, if somebody owns a lock and they die because somebody does a cog stop on them, we can't have the lock marooned, right? So these locks actually free up. If the owner dies, the lock becomes free. So it makes stuff like this more resilient.
So if the cog stops, which kind of uses the lock gets freed automatically.
Right.
Yeah. Okay.
Yeah, that's just that's a quality of the new locks. That's just how they work.
Cool.
Here's another question. So there is hardware support ultimately to be able to control single stepping and query RAM.
Correct. Yeah, it's all in the silicon. We can single step. We can break on address. We can break within interrupt 1, 2, or 3 code. We can do asynchronous breakpoints, but you need to do that from another cog somewhere else that is also in a debug ISR. So it could be, I mean, so that's a little tricky. So if you want to do an asynchronous breakpoint, you know, a random breakpoint on someone else, you have to do it from a cog that's already in a debug ISR, because all this stuff is protected from the normal world once it's set up. But the way it would work is to have like an interactive debugger is one of the cogs would vie for the serial port. So we'd use a lock to denote both that would control both P62 and P63. And then a cog would send out a message, and then go ahead and do this, jump to this location, or put this data into this register. It could also be like, don't do anything yet. Just ask me later. So he releases, because the way it works when you have people, you know, you're waiting for them to press a button. Meanwhile, the thing is sitting in its debug interrupt all locked up, but the serial port has to still be shared with all the other processes. So we have to come up with a little protocol for sending out queries to the host, getting responses back, even if the response is, I don't know yet, ask me later. And at that point, you release the lock, wait for, you know, a couple milliseconds, and then get the lock again, and then do the query and response again. So it works without any kind of centrality. It's all kind of a peer-based system. The only connector would be the host at that point.
So I'd like to know if any of the people visiting on the live forum are going to put this to use in the next day or two. And then also, Chip, where you're going with it next.
Okay, let's see. DeMaio asks, is the Spin2 debugger actually added to the source and compiled all together? Or Peanut has a binary blob? Yeah, Peanut has a binary blob that's added to. And that binary blob has like a few longs in it, which the compiler has to set up to configure it. So it's not actually going out and, you know, compiling or assembling the debugger, but it's actually taking the binary blob, tweaking it a little bit and then attaching it to the front of your application so that when that blob gets sent down to the whole blob gets sent down to the chip, the first thing that happens is the debugger's running. So it installs itself into high memory, sets up the debug interrupts, moves the application back to low memory where it's designed to run, and then it fires it off. And then as cogs are started, these debug interrupts are occurring. And each time they occur, they hook the next interrupt. You know, they set the condition for the next interrupt. So Ray Allen says, okay, he'll use it. That's good. Now, okay, someone is wondering if FastSpin supports this debug yet. I've got the code there. So, you know, Eric Smith, in that case, he could see how it works and I'd help him integrate it. The only trouble is it's not like a little concept that stands all on its own. There's a lot of integration with the language system to make it all play. So he would have to come up with his own variation of what I did in order to fit it into FastSpin. But it's totally possible, but it would be a little bit of a project. Just reading these things. Okay, let's see. Someone asks, is it, or possibly, wait, is this a continuation? Can you add more than one serial out? Not at the moment. Or is this best handled by the user if they want to add another passive device listing on the TX line? Yeah, I'd probably do it that way. Or possibly see the last string debug sent out. Is it stored and return a pointer to that string so we can manually send that to another display for formatting? So here's the thing. That string never exists. I mean, the string that gets sent out, it gets composed as it's needed for sending. It doesn't actually exist in memory anywhere. But I mean, you know, I suppose it could be made to operate that way.
Okay, last roundup for questions. Then we'll stop and upload to YouTube.
Yeah, Ray, I have one still. Since the debugger kind of gets added in front of the whole file, you basically lose 16K of available file size.
No, it's not that bad. The debugger is, let me see if I can run it here. It's like, hold on a sec. Right now my cursor's gone missing. Here we go. Let me look at it really quick here. I'll tell you how big it is. I'm gonna load in the debugger. All right, it's called Spin2 debugger. Here we go. So the debugger is 1216 bytes. So what gets prepended to your application is this 1216 bytes plus the debugging database that gets ultimately moved up to the 16K, and then the whole application. So to the download, it adds 1.2K plus, I don't know, maybe 100 bytes for all of your likely debug statements. So it's under 2K that gets added to the download.
Okay, that is not dangerous. Yeah.
Yes,
but basically, when I understand you right, I could kind of take any cog I have left and install some finer debugger in there, which is then able, if it is itself is in a debug interrupt, to interrupt other cogs.
Yeah.
So
yeah, you could do that.
Could write one dedicated debug cog object, which then gets loaded, uses one cog, but is able to interrupt every other cog when needed, kind of when observed.
Yeah.
Yeah, that's
Yeah,
nice.
if you want to have that asynchronous breakpoint capability at all times, you do need maybe a dedicated cog that is just there to interact with. But what it could do is it could take the band load, the band load or the bandwidth demand off of other cogs for a debugger.
Right. Yeah. And that thing could kind of be way more complicated than the simple debug output is now. I mean, that could set breakpoints at addresses and.
Yeah, the trouble is, once you start getting there, because I did this before for the SX chip, like back in '96, and we made a full single stepping debugger, and it becomes really like immersive for the user. You have to present everything to him and then get his response and then do stuff, and it's like it's not trivial to set up something like that. But we'll get there. I'll work on that soon, I think.
Yeah,
So
but
an error message that I got first time that I ran it, I opened up, what was it, blink.spin2. I ran the debugger, and I got an error message that said, debug requires at least 10 megahertz of crystal external clocking.
Right. Yeah. What you were doing is you were trying to debug the debugger program that I put there just for so people could see the debugger. So that thing doesn't get like run in the normal sense. I assemble it and then I pull it into my application as a blob. So I need to come up with some instructions on what you do with what files.
Yeah,
Chip, I think
I just mentioned it because it's going to come up on the forum. Somebody's going to see that message and wonder what it's all about.
Yeah.
I think he was running the blink.spin program, which doesn't have any clock setting in it.
Oh, okay.
So I think that error message will go away as long as you configure the clock for at least 10 megahertz. Is that right?
That's right. Yeah.
Yeah, it was just a blink spin 2 program.
Yeah, I just put in a con block, put underscore clock freak equals 10 million, and it'll take care of that.
Hey, Chip.
Yeah.
So the binary created with the debugger is a .bin2 file, right?
Yes.
So if I try to run that with load P2, is that going to run?
Oh, I don't know. I got to think about this. When I don't know that my tool, I'll have to look at my tool. When it appends that thing, let's see, it happens right in here. Let me see what I do here. I don't know that when I'm saving it. Let me just look really quick. Okay, so what it can do is it inserts the debugger, and then on top of that, it kind of prepends the debugger onto your big application. And then even after it's done that, it can prepend the Flash programmer onto it also. Because these things you can just stack them up like, and each one does its thing and then moves the other guy down into low memory and fires him off. So let's see, when I'm saving, I do the insert debugger. Yeah, it does save it as a .bin2 file. Yeah, it does. I didn't know. I think I might have put that in there just for my own debugging purposes, but it's there. It makes a .bin2 file with the debugger on it.
Okay. So does something like load P, any other loader that we use, it's going to load that into the P2. Is that going to be able to launch? Is it going to be able to execute right off?
Well, yeah, it starts sending data out on the serial port. That's what it does. So
it might be a little off there. Because load P2 is going to load and then try to bring up the serial terminal, so it might be a little behind, right?
Oh, well, you know what you can do is you can do the like Control F11, which is the Flash program with debug, so it's both.
So okay,
And then all you do is you hit reset after you get your serial terminal
Right.
up, and it all goes.
okay, I'll try that.
The thing is, those messages come immediately because as soon as we're done downloading, within like, I don't know, a couple of hundred microseconds of that, the application starts running. And then the first thing it does is cog0 boots, right? So that creates a cog0 init message that comes out right away, long before maybe any of your debug statements do anything.
So we can miss the beginning of that, basically, is all.
Yeah.
Okay.
But if you program the Flash, then it doesn't matter. Anytime you reset, it starts from scratch.
Right. Okay. Thanks.
Yeah.
And Chip, what's the state of the documentation? I pasted a link in a while ago.
It's all up to date now. There's nothing that in that Spin2 document, all the debugging stuff is covered, the language is covered. I updated the command line interface. You can do like program Flash with debugger from the command line. So you don't have to be in the app and working with it. And then there's also a new instruction called clock ASM, CLK-ASM, which is a PASM instruction, which actually acts as a macro. So whatever you configured the clock as, it'll set up the appropriate sequence. And for crystals, it's a 6 instruction sequence because it has to load the initial pattern minus the 2 LSBs so that it still runs on the RC fast while it revs up the main clock. Then it does a wait for 20 million, or no, for 10 milliseconds, I think. So it's like a 20,000 count wait. And then it does another 32-bit hub set with the main thing. So it's a 6 instruction macro, but it makes it easy. You don't have to keep typing that stuff over and over again. And if it's RC fast that you've set up, it's just 1 instruction because it doesn't need any special. Or RC slow is just 1 instruction.
All right, one last question from Clouseau. Can a delay be put into the debugger to slow the initialization?
Yes, certainly. I mean, I could add that from the compiler too. I could use, let's see, make TX pin settable. Also make initial delay settable. Via symbol.
And Chip, going forward for more feedback, what forum thread are you going to be watching? Peanut forum thread?
Yeah. I'm just kind of, all I know is the forums. So, yeah, there's a thread called latest P2 version. That'd probably be the good place to talk. Let's see, I'm reading these comments here. Make sure you had con. Let's see, referencing range, accessing the debuggers. Yeah, all the instruction in the new Spin2 document, the whole this debugger is covered. And then in the main chip document, all of the debugging hardware is covered too. So, you know, there's enough detail in this that I can't remember it all. So when I design all this stuff, I go back and read that Google Doc because that's where that's where all the information is.
Chip, can I make a comment? About smart pins. When are you going to make us some real life examples on smart pins and give us a little documentation on this? It's one of the most fascinating parts of the P2.
Yeah, I know. We need to get that going. We need to start writing some objects for applications, and then Ken's really hammering me about that. That's what we need. And
I've done the really easy ones.
Yeah.
Well, we just want some real world examples just to get started. So, you know, we can. It's just too complex for most of us to even start.
Well, you know, every time I go to use a smart pin, I get stuck. I mean, there's some detail I'm not remembering straight or something. So I always go back to that big Google Doc. And the code is never big that's required to make the smart pin do anything, but there's often some little detail that I wasn't remembering that needs to be addressed. So yeah, we need to see what I want to do is get the tool to a mature enough point where I can write code for it that will last, without going back and changing things later after we have a significant code base. I don't want to be doing that. And that's kind of already happened a lot as it is.
One of the upcoming presentations is what John Titus, he'd like to talk about smart pins and all the documentation you made. So that could tie in.
Yes.
Make some nice demos, yeah.
Yeah, and it's about demos and how it works, applications. Where else would you like to allocate Chip's time?
Oh, any kind of demos. I mean, we love demos.
On chip compiler.
Yeah, well, I started writing a parser. I have the whole Spin2 language symbolically in this parser that I wrote. So I could write that whole compiler in there. And the code, I think, winds up being smaller than it is on the PC. Right now, the 8386 compiler that does all this stuff, it's like 14,500 lines.
Well, how about translating it to C and then compiling the C for the P2 and for PCs and Macs and Linux?
Yeah, I know.
And PC, with C, it's supposed to run anywhere, right? I mean, that's what my C friends tell me all the time.
Right. Roy Alton had made that for the original P1, but yeah, this is a lot more complex. I think that this compiler is maybe, I don't know, 4 or 5 times as complicated as the original.
Okay, so maybe we'll wrap it up, Chip. Awesome work getting this done on schedule.
Yeah, okay, so DeMayo's asking real quick about timestamping. Yeah, we could do that. The timestamp should be recorded the minute we come into the debug ISR, not after we've waited around to get the serial port handle, right? It needs to be, we need to grab the timestamp immediately, hold on to it. Once we have the serial port, we can incorporate it into the message. So that's doable. It's not hard. The only problem is that right now I have I think none to 1 instruction left. When the debugger comes in, there's an initial 16 instructions that get put off to that protected memory, and then a little program gets loaded in and run. And that program in turn saves off registers 10 through FF into part of that 16K block, and then it loads in the main debug program. So at the moment, let me just see here. Is this my, let's see, I have 2 instructions left. So it's not enough to do a timestamp. What I could do is make this thing kind of shuttle, like have part of the register space be flexible so that I could load different routines in it that are needed at different times. But right now it's just one whole program that gets loaded into register 0 to register FF. And I'm out of space.
Okay, we'll move you to smart pins.
Chip, if you change get sec to get millis or whatever, we talked about this before, then couldn't you stick that in a debug statement? So at least for your timestamp, you could have your milliseconds from reboot.
Oh yeah, well the way we do that delay is because the compiler knows what the clock frequency is, because it has to be known, otherwise we can't configure the serial port, right? So that's known at compile time. So it actually computes out like how long of a wait X value do we need, including looping overhead to get exactly 1 millisecond. So I can put constants from the compiler into that little blob that gets prepended.
But you said we could put a function call into the debug statement, right?
Yeah.
So for spin debugging, if you had get MS versus get sec, which I don't think is very useful for differential timing, then we could stick that in and at least have that as a flag.
Right, right.
I'll send you an email.
Okay.
Yeah, to remind you, because that, you know, I'm obviously very happy with Spin 2 and writing a lot of code and having fun with it, but that that function to get the seconds since a reboot is not terribly useful. It would be much more useful to know the milliseconds since reboot.
Yeah, the trouble with milliseconds was that 32 bits worth of milliseconds goes by in just a couple of months or something.
Yeah, but,
So
but that's not a problem. It'll roll over. I do this all the time.
Oh, yeah.
It's not functionally, it's not a problem.
No, I don't know that it would roll over. There's something funny that's going to happen at the end because we wind up with I think we wind up with a strange remainder problem. I have to think more about it.
Okay, but because you know, again, I'm sorry to be, I don't mean to be harsh, but get seconds is ridiculously unuseful.
No, I know, but
not useful at all, and it's just consuming compiler space or interpreter space.
Yeah, well, but it doesn't run out soon, so you can, if you
but nobody uses it, but there's no point in having it.
It's like 3,000 years or something, or 3 years.
It's 2,900 years. I calculated it once for my article. Because I have a nuts and bolts article. So for the group, I wrote a P2 article for nuts and bolts that's coming at the end of this month. But there's a couple of things in there that we thought we're going to have that we don't. So we'll deal with that from readers. I'm sure they're going to say, hey, you said this. So things changed. I do say in the article, look, this is all very fluid. And, you know, we have the opportunity to change things. For me, I think it's great that the interpreter can be modified past the silicon production. That's useful. And what we have in the P1 is fantastic, but can never change. That's nice at the P2. And I think very long term, you know, I think having, now this would be on you, Chip, that, you know, showing people is like, hey, if you want to create an interpreter for another language, here's how you do it. Mm-hmm. And install that interpreter versus the Spin 2 interpreter.
Yeah, it's all flexible.
Yeah, exactly.
Hey, one thing I kind of like, I mean, I like the potential for not having any delays, because ultimately I want to have the tool so that, you know, you hit the key to run and things happen within a split second. So there's never any multi-second waits for other stuff, but it means that the tool has to be tightly integrated. But one thing we can do with this debugging, right now we're just sending out messages, right? I'd like to make a little graphical thing so that you could set up like, say, a scope display with persistence or something, and then give it an actual name, and then give it some channels and some colors, all textually. You can figure this all textually, so it's kind of system agnostic. And then as you spit out these messages, they can go into these channels, these virtual channels, so that on your PC, you can have nice like XY displays, rolling scope displays, you know, pixel displays, whatever you need, because we can report messages really quickly now, right? So it'd be nice. Oh, go ahead.
It takes time to set up, like at the moment, if I'm using PropTool or anything to compile a P1 code, I always have a delay in there to allow me to then set PST running. The one thing with Eric's compiler, which is the same that we had with BST, was that the moment the code loaded, it could run immediately because it opened a serial window directly. If you've got to open a serial terminal, PST is ideal because you can switch backwards and forwards between PropTool and PST, and it'll relinquish the serial port. Whereas if you've got Terraterm or one of those, they won't release the serial terminal when it loses the focus.
Oh yeah.
There's pros and cons with that.
Right.
Because obviously you can't do anything else while you've got PST there, or you lose the terminal. But But the big thing is you've got to put a delay at the start of your code, and that's why we need a delay option to execute the debugger.
Mhm.
Chip, are you suggesting a kind of an advanced version of PST that would allow the terminal to interpret data in the debug stream to create a graphical output?
Yeah, that's what I'm talking about. Yeah. I mean, someone can make this tool. It's not just for a P2, it's for anything, you know?
Yeah.
Just some way so that through serial COM, you can like define, you know, display types and name channels and colors, and then feed those things subsequently the data to make them come to life. So if you're doing DSP stuff, it would be really nice to be able to see things as they're changing in some kind of, you know, representation that makes sense.
That will be better done from the P2 displaying it onto a VGA screen, because the problem you've got is at the moment you put Windows back in the mix or a PC back in the mix. If you've just Windows, then it's not platform independent, and if it works on all of them, you've still got that delay. Whereas P2's capable of having a cog running just displaying the data out of a window in Hub, and VGAs are a dime a dozen. You can pick them up on the street for someone's trash. So the P2's capable of it. Let's use it. Let's not lock ourselves into platform dependencies.
Hmm.
And I don't care if it's the second P2. If we get to the point where we need it.
Right.
Yeah, I'd also like to do the debug with the HDMI display.
Well, yeah, if you do it on the chip, it's nice because there's no latency and it's super high bandwidth.
I was thinking about, we have the PLX DAC tool for Microsoft Excel for streaming data in, but that's going to be slow as well, isn't it?
Yeah. The one thing with HDMI that I keep on looking at is because it requires such high bandwidth, VGA is real easy to output on a small group of pins. The advantage of the HDMI is the connector, but I can't see a way of using an HDMI connector to run VGA. Because I'm talking about outputting VGA on an HDMI connector, not outputting HDMI and then converting back to VGA.
You know, what I really like a lot is the component video for HDTV with one signal. Like, I'm going to run a program here. Let me get my monitor. Where's my remote?
Chip, not to sidetrack you, but getting back to this HDMI display and using it as an output device, we have this driver, which I've seen bitmap graphics running nicely. What about text display with the tool you produced?
What do you mean, what about?
Well, do we have an object that we can use to use the debugger that you're showing today with an HDMI display?
You mean, well, yeah, I mean, you could take an HDMI program and add some debug statements into it. Is that what you're asking?
Yeah.
Yeah, I don't know. Yeah, it may not. I mean, the performance is going to pale compared to what a big, you know, live screen is going to give you, but you could.
You're just talking about putting text display on the output, aren't you, Ken?
I am, yeah.
Yeah. Well, that's just running a font interpreter into a piece of hub.
But the debug code is wanting to send serial out on a specific pin, whereas the HDMI monitors are looking at a different physical output. So is that where is?
That's what I'm asking.
Create a complex, yeah, because it would be nice. It's probably very complex, but you know, if you could say, hey, I want it to use this kind of output mode. The way, Chip, you've got that mechanism for using the send method. You can declare it to be a function, and then it takes care of it from there. it would be neat, although probably very difficult, if debug could do the same thing, where it's, if you want to debug to the terminal, you're doing that. You want to debug to HDMI, you're doing that. But again, probably more complexity than you want to deal with right now.
Yeah.
It seems like you could just have a pin, sniff the serial output and just display it on the HDMI display.
Oh, that's true too.
Yeah.
Yeah, because you could have a background cog that's just watching that debug serial pin and echoing whatever it's sending.
Let's see here. I want to show you.
Best solution will be a second P2 with a HDMI monitor on it, keyboard, and that thing can do it. Kind of a new project, debug.
And
Yeah.
Peter's down in Australia saying, I could knock that together and tack on in about 10 minutes.
Well, I think some of the MicroPython work is pretty close to doing that because they've got mouse, keyboard, display, and then MicroPython in one cog working nicely together.
Yeah, and use that as kind of debug terminal and attach it to one pin.
Yeah, someone will come up and say use a Raspberry Pi, but let's use a P2.
Yep.
You see this? This is 1080p in component, right? And look at this. I can pull off the colors. Okay, there's the here's the blue. Now look at this. This is one wire. Can you see that? That's it. And look, it makes it a whole monochrome screen, 1080p. So component video is pretty cool. I mean, it's just one pin, and you get better resolution than you can with HDMI on our chip. Now, if I plug these things back in, we'll get the full. Man, now we're back to like cyan.
That's great going to a TV, but what I'm suggesting is that there's monitors sitting on the side of the road that have got VGA connectors. Right. They don't all have HDMI, they don't all have DPI, they don't all, and certainly most of them don't have composite. And they're the cheapies that I've got. I mean, I've got 3 24-inch monitors here. They've all got VGA. Some of them have got DVI as well. Some have got HDMI as well, but they've all got VGA.
Yeah. No, I like that kind of thinking, but I also realize that people need something that can be also kind of portable. I don't mind setting up my workspace. So I've got all kinds of monitors that I can plug in and do all kinds of stuff with. But a lot of people, they're not going to get past their laptop. That's all they're going to have.
Well, Peter, why not use an HDMI to VGA converter?
Because HDMI is much harder to output, requires much higher frequency, whereas VGA you can do it at a much lower frequency and you haven't got all those hassles with cables and everything else. The bad thing about VGA is it's a horrible connector. But you can, I mean, you could generate, with a couple of resistors, you could generate a single pin coming out and converting it back. Food for thought.
Well, what I wonder about is how long VGA will be around.
Well, it's still on every modern monitor.
Ken, this is Jim Schaefer. I've got a whole junk pile full of electronic parts and stuff, and went looking, and I've only got one very old VGA monitor. And they may be readily available at Goodwill stores, but I've only got one that I could even touch. So in terms of display, HDMI going forward would probably be a better choice. But Peter, I understand your point that it requires so much bandwidth.
I'm certainly not seeing it out here in Australia, any monitors that don't have a VGA connector. They've all the new ones have got HDMI granted. DPI has been dropped, but all the Dell monitors that we use at work have all got VGA inputs.
Well, now I'm trying to pick up my monitor and look behind it.
Yeah, and there's no standard place for the damn things either.
Well, I find it very easy to interface to VGA monitors, and because I just use a few pins on the board, I don't need to worry about a VGA connector or anything. It's a bit like a serial port. It doesn't take up much in the way of hardware resources or software, etc. So that's why I like to use it like that.
Okay, well, why don't we wrap it up? We're coming up on 2 hours. And thanks, Bob, for jumping in, taking control with the computer.
Yeah, thanks a lot, Bob.
Hey, anytime. I learned a few things.
Thanks, Chip.
Yeah, thanks a lot,
Thanks,
Chip.
guys.
Yeah, thanks, Chip. It was excellent.
All right, and see you all next week.
Okay, guys, thanks for coming.
Thanks, guys.